Good afternoon. I will talk today about the lessons learned with Hawk this year. The most frequently asked question has been, the blue needle shows a larger value than the red needle. Why? The first answer is it's not a bug. I will demonstrate that the algorithm correctly computes the result, but where this difference comes from. We've learned a lot from aerodynamics in these years, and that is the base for understanding Hawk. Of course, for the user, your only interest is in how much does the glider climb in meters per second. But to understand or to fully exploit Hawk, you need to understand why the blue needle, or the potential climb rate, as we call it later on, is much larger sometimes. Okay, let me first start to recapitulate what Hawk does and what the tech warrior does, because they are complementary. First, Hawk computes the three-dimensional air mass movement based on a complex algorithm using multi-sensor fusion. So what he compute here is the vertical axis of the three-dimensional air mass movement. It's a climb rate of the air mass, typically called netto. I don't know for what reason, but it's called netto. From the netto, of course, yes, we have the two-dimensional, what is commonly called wind is here. So this gives the three dimensions, importantly, in real time. No averaging, real-time computation. Okay, let me go back to the climb rate. From the climb rate, we subtract or compute the real sink rate and obtain the climb rate of the glider. If you view it as a triangle, then we have here wind, to airspeed, v ground. That's a bit difficult to understand, but that's what it does. Okay, excuse me. Now, this is what Hawk does. We then do the following to get the so-called potential climb rate. We take the climb rate of the glider and subtract the sink rate of the polar. The sink rate of the polar is an ideal quantity measured or computed under calm air, totally calm air. It's an ideal result. Let me see, yeah. And you see here that the sink rate, the theoretical sink rate, is then climb rate, sorry about it, climb rate minus theoretical sink rate equals the potential climb rate. Potential means this is the best climb rate you can obtain for this climb rate of the air mass. Now you see from these two figures here that the real climb rate, the real sink rate is much larger as the theoretical climb rate. Where does that come from? We'll see there's an aerodynamical effect, which is the reason for this difference. As I said before, you're mostly interested not in the potential climb rate, but if the potential climb rate is much larger than the climb rate of the tech vario, then there is information which is very important or useful to use. But of course, I first need to say what the tech vario does. The tech vario measures with a totally different principle the climb rate of the glider, actually the climb rate of the glider. And as I just said, if this climb rate of the glider is much smaller than the potential climb rate, this means we do not optimally use the size of the thermal here. To understand that, sounds complicated, we need to go to understand and have a look at the time varying signals. But first, the summary. Hawk and tech vario are complementary. Hawk is not a better Tech Warrior and Tech Warrior is not an instrument to measure the climb rate of the air mass. They're complementary. We'll see later on. Complementary mean in circling, we can use both of them in a dual instrument. All right, now let's have a look at the time varying signals. Here is the altitude. Here is the blue and the red needle through airspeed. Wind is here, horizontal wind is here. Okay. And what you see now is not IGC data. This is the data which we collect a sample at a very high data rate and later on play it in a computer in the lab. So let's have a look, and please look at the wind, the climb rate, and the different behavior of the blue and the red needle. What you see here is the wind, the heading, the blue one. You also observe here, we'll see later on another example, that the wind is steady. If you fly in the mountains, this is not the case. It's not always the same or straight value. Now, okay. Let us see now what the results of the average of the first slide is. The climb rate of the glider measured from GPS is 1 meter per second. The Warrior Hawk shows 2.1 meters per second, which is optimistic or larger. That's the potential climb rate. The Tech Warrior is close to the real correct climb rate of 1.0 meters per second. Where does that 2.1 meter comes from? We see the sink rate computed in the algorithm is minus 1.8 meter. If you go to the polar, it's minus 0.7 meters. So there's a difference. And if you subtract that from that, you get within statistical accuracy the result of the Warrior Hawk. Okay? So you see the difference here. And what causes this additional sink rate? Because to understand Hawk, belief is nice, but understanding and the proof is another thing. Okay, aerodynamically, we explain the so-called plateau effect of modern profile. This is what we learned from the aerodynamicists. We know that Hawk also shows a larger climb rate because of a too large side slip. 3 to 4 degrees are absolutely tolerable. That's what we do in flying, rain and bugs. And also should be mentioned, if your static or dynamic system is not properly installed, then you will also see false results. Okay, now let's have a look at the aerodynamics to explain. An important, probably the most important quantity in of the wing is the angle of attack, shown here. The angle of attack is the flow to the wing. So we have a line here of the wing. We have our triangle. This is the ground speed. Yellow is the true airspeed, and D1 is the wind. This is a vertical component, a burst, a gust of the wind. This is from the safety report of the crash of the 52 a couple of years ago, tragic crash, and the explanation what happened because of these gusts. So you see, if it's a negative gust, then the angle of attack is here. So let me see. Yeah. What happens now if you have a positive gust? we safely may assume that while the ground speed here is about the same within a short interval of time, we see the burst, the gust here causes the true airspeed have this direction. Remember, ground speed equals wind plus true airspeed. Now you see that this is what is critical and important is the angle of attack here, the yellow one, is much larger. And this is what caused the stall of the flight of the aircraft here. And this is also very dangerous in gliders if you fly in the Alps or in the mountains and close to a ridge, too slow, and bursty nature of thermals, then your angle of attack increases. And that could be dangerous for a stall. Okay, what is now the climb? What is now the, let me see, yeah, what is the so-called plateau effect? We've seen that the vertical bursts or gusts causes an angle of attack here, delta alpha. We fly this here. Now, let me first introduce, of course, what is plotted here. This is the lift coefficient. This is the angle of attack, okay? The larger the angle of attack, to a certain extent, the larger the lift, the lift coefficient, and the better, and the higher, the more, yeah, then the better the glider climbs. Usually you go close to this point here because there's the maximum climb rate within limits, within safety limits. Now you see the old profiles here, they had this shape. No plateau effect occurs. The modern plateaus, very specifically different from plane to plane, they have this plateau. i.e., if you change your angle of attack, nothing happens. And for example, somebody who has flown an AH-25 knows during landing this is not a nice behavior, because if you're not very careful, then it just dumps down. Now, okay, let's go back to aerodynamics. So let us assume this is the point of operation on the average. We have positive changes due to a positive gust, and we have negative one. Now, it's important to understand, even if these changes occur equally probable, so as many positive as many negatives, the effect is a negative additional sink rate. Why? If I have a negative burst, then we go down here and we see, okay, it's the climb rate is less or the sink rate is larger from here to here. What about the positive burst? Hopefully we would hope, well, if it would generate an equally large portion additional climb rate, but it doesn't because of the plateau. So the effect here is 0, basically, and here it's negative, and adding it up makes a total of negative. And this is the additional sink rate which you observe. The literature of the aerodynamicists is down here. Now, this is interesting to see it in the other tool we have with Hawk. How large is this effect? Negligible, or do we have a real change in the angle of attack? Here is altitude. Here is the air mass movement. Here is the angle of attack. Now let's have a look at it. We see that in this fairly turbulent thermal, the climb rate, the netto, varies within large portions from 5 meters to 1 meter. This here is one circle. This is the next circle. Okay. And also the angle of attack changes from 9 degrees down to 1 degree. So 7 or 8 degrees, and this is huge. If you're not careful, the plane will stall. Okay. Back, I hope I tried to explain it, that the changes in the angle of attack have a different result in the negative, responding to a negative burst than to a positive one. Of course, what we then did is to experimentally validate these findings. We analyzed a large number of flights with different pilots, different gliders. And what you see here is the difference of the Vario Hawk, the potential climb rate, and the real climb rate of the gliders. That's the difference. So 0 is here, 0.5 meter. Here, the potential climb rate would 0.5 meters per second larger. Here, 1 meter. Here, negative. Of course, statistically also negative results must occur. But let's have a look at it. It is plotted here. How often does that happen? We see here the difference between 0 and 0.25 meter occurs roughly 30%. The larger difference is between 0.25 and 0.5. Well, it's about rough. We'll go over here. It's about 15%. But we also see even large, 1 meter or above, is possible, though not very likely to happen. These are experimental results and which show the effect really is there. Okay, now I focused so far on the most frequently asked question: why is the potential climb rate larger than the climb rate, the compensated climb rate of the glider? I hope that could answer this question, because that's very crucial. And understandably, a lot of people were concerned, said, well, this instrument doesn't show, it's too optimistic, doesn't work. It works. Now, hopefully, if you fly and you're not a beginner, then your percentage of circling is below 20% in a good day, far long, okay? Therefore, we also need to consider the behavior of hawk during these 80% of time. And that's where the real differentiator is, which no tech Vario can cope with, because the tech Vario by construction shows these false alarms due to horizontal gusts. I'll demonstrate you this here in this movie. Here's altitude. Here are the 2 pointers. And the glider is moving here. Let's have a look. I would just ask you to look at here, the 2 needles, and see that the red needle badly responds to horizontal gust. Let me go. Okay, here. There is no, the hawk does not respond. And the altitude does not respond. So this is very important. If you fly cross country, these avoids unnecessarily surge cycles. And that's a major strength of hawk. No false alarm. If hawk shows a climb, there is a climb. That is demonstrated in the next slide. Namely, the other important feature or property of Hawk is if there is a thermal, Hawk doesn't miss it. So this is called detection probability. The other was a false alarm probability. And now again, please look at the glider approaching the ridge here. Okay? And look at the blue needle and the red needle only. Here, Hawk shows you, okay, there's the thermal coming. Look at the altitude meter. Later on, with a false reading, Hawk follows, the tech follows. Then they shortly agree. Okay. Let's run that again and also look at the wind. Okay, let me summarize. The most important and really innovative step is Hawk does not respond to horizontal gusts, no surge cycles. Second, warning, a smooth early warning to get into the thermal. And remember in slide 1, the complicated inflow and outflow of into a cloud or in a ridge here can only be exploited with the real-time processing of all 3 dimensions. Okay, let me summarize. We advocate or propose, for the reasons explained, a dual instrument. And let me explain what we mean by that. I tried to explain that Hawk and TechVario are complementary, like the red and the green color. In cruise, you only need Hawk. You don't need the TechVario. It just gives you false readings and is too late. This is the major strength here. Different story where we invested a lot of time in this presentation is, what about if you're circling? Okay, if you're circling, you need Hawk and TechVario. Vario or Netto? What you can do is, here different approaches are possible. From the feedback, every pilot somehow has its own style. You can, for example, fly with a blue needle, okay? Hawk, Vario. Blue needle. To obtain the climb rate, you can use an F boxes. That's one of often found approach. The climb rate of the TechVario and the Hawk Vario, you can compare. It also, you also have your personal adjustments to the audio. What I want to say by this slide is there's no simple rule which one size fits all. Different pilots, different attitude. Okay, so this is what we propose. Thank you for your attention. I hope it has been useful to you. Thank you.